The next related rate problem I want to look at with you is number 13. This is in the homework part of that ginormous handout. And this is one you haven't studied yet also. So you're going to be reading and rereading it quite a few times. Go ahead and listen in. We have a revolving light located 0.5 miles from a straight shoreline. If the beam of light is moving at 2 miles per minute along the shoreline, what is the angular velocity of the light at the time when the beam is 1 mile from perpendicular? Very confusing situation, something you may have never thought about before. So let me try to help you enter into this problem. So what I want you to think about here as you try to gain entry to this problem so you can start picturing it is, are you familiar with the idea of a police car? You've seen those before? Okay. So police cars used to have these lights on top that would have a spinning reflector. So if you watch really old TV programs, you know what I'm talking about. This is kind of the same general idea. So this is a modern-ish lighthouse, and if you've never been in a lighthouse, they've got that same kind of thing where they've got a reflector, and that reflector can rotate around, and it creates like a strobing effect. Like if you're familiar with what a strobe light is, that's the general idea where you occlude part of the visual space, and then the light shines really brightly again, and that's what creates that strobing effect. So I won't demonstrate it for you because sometimes that strobing effect is linked to people that have motion and other types of vision ailments, and I don't want to trigger anything like that. But that's kind of what we're talking about. So right here at this lighthouse, we've got a thing that's spinning around, and as it spins out to sea, you can't see it on shore, but then it spins back around, you can start to see it on shore, and at some point in time, the light is perpendicular to the shore, and then it keeps going along the shore because remember, it's rotating like this, and then once it passes some point where it's no longer on the shore, you can't see it again, and then it comes back. That's kind of what the situation is talking about here. Hopefully, when you have related rates on your AP exam, it's not quite as difficult to picture. But anyway, let's talk about what's going on. So this is really a difficult question to figure out what to do, but I feel pretty comfortable looking at this, and since it talks about the perpendicular, thinking about how this is a right triangle. Make sense? Okay, makes sense, right? Right triangle. So because I know that I've got a right triangle, I immediately start thinking about things like, oh, the Pythagorean theorem, any of the trig guys, whatever. Sine, cosine, tangent. Those are what I start thinking about when I start thinking about this type of situation. So I arbitrarily decided to use A, B, and C. I'm going to say that A, B, and C works like this. So A, that is perpendicular along shoreline. That's that distance. B, this is the distance from the shore to the lighthouse or vice versa. And I'm going to say that C, there's lots of ways you could describe it, but what makes sense to me is just call it the light beam's length. All right. So that's what A, B, and C are. A is, or dA dt is the change of that distance, dB dt is the change of that distance, dC dt is the change of that distance. If I were to differentiate the a squared plus b squared plus c equals c squared, I'd get the same equation we've looked at several times today, as well as other days. And tangent, sine, and cosine would be very similar to the rocket problem we looked at earlier as well. But the angle is this angle right here. So that's where theta is. And it's this angle right here, the angle that the lighthouse makes from the perpendicular along the shore. So d theta dt is the change of that angle. But the question is asked in such a way where it says angular velocity. So I don't want to get too far into the idea of angular velocity with you or spend too much time investing in physics. And do not do this in a physics class. I'm just doing this because it's going to help us understand what we're doing here. It's not technically correct. The rate of rotation. That's what d theta dt actually is. Because remember, it's the rate of change of this angle, right? The one that I've marked here, as we go from the perpendicular along the shoreline, and then we rotate around and come back. So that's why it makes sense to call this angular velocity. So the reason why we use velocity is because there's two directions of rotation you could have. You could go this way or you could go this way. So you'd have to define one is positive and one is negative, depending on how you're doing that. So anyway, we're really only interested in this very short snippet of it. So it's kind of weird, but that's what we're trying to figure out. So that's the connection, d theta dt. So as we look at all these options here, which option makes the most sense? Pythagorean theorem, sine, cosine, tangent, which one? Which one's going to have in it what we're looking for? And it seems like we ought to be using something that has a theta in it because I want to differentiate the theta to get a d theta dt. So which one makes sense? Honestly, you could work with any of them, but I think what's going to be the easiest to work with here is tangent. So tangent is going to be a divided by b. And if you're curious about why I chose tangent, that's because the light is a half mile from the straight shoreline and the beam of light is moving 2 miles per hour along the shoreline. And the beam is 1 mile from perpendicular. I have a value for B. And I have a value for A. Oh, that was an inopportune choice of color. Let me change that. I was about to get a little bit more confusing. So that's why I thought tangent would work, because I've got A and B. And similarly, I've got a dA dt, dA dt. That one is this, and it's positive because that distance is increasing. And believe it or not, we have a dB dt as well. It doesn't tell us what dB dt is, and I don't have to calculate what dB dt is, but I know what dB dt is. And you may know what dB dt is also. That is 0 miles per minute because the distance from the shore to the light B doesn't change. All right. So I know which equation I'm using. I'm going to differentiate it with respect to time. And I'm going to get all my stuff and I'm going to put it in there. Okay. All right, so we're gonna stop that one right there. So we can look at something that may be familiar, not familiar, difficult, not difficult, hard to say. But I want you to take a little bit of time here with number 16. When I say a little bit of time with number 16, give it 2 minutes. Invest 2 minutes in the picturing / reasoning process. That way, when I go through it, you might have some things to connect it to. Thanks for checking that one out. I like reading, so I'm going to read. Water is poured from a dispenser into a paper conical cup at a rate of 2 cubic centimeters per second. The cup has a height of 15 centimeters and a top radius of 5 centimeters. Find the rates that the water level is rising when the water is first 2 centimeters high and then 12 centimeters high. How do you account for this difference? Okay. So what are we thinking here? Well, we're pouring water into a cone, which to me sounds like volume. And the formula for volume is 1/3 pi r squared h. And the derivative of volume with respect to time is 1/3 pi r squared dH dt. Plus 1/3 pi times 2RH dr dt. So that's one way you could do it. Now, something you need to be very cautious about, just like for the one we did earlier. Yes, we've done pretty much this problem already. Is we're talking about water, not the tank. This is not about the tank, this is about the water. So why do I raise this? Because if we're doing the tank, dH dt, dV dt, dr dt, those are all 0. R, the radius of the tank, is always 5, and H, the height of the tank, is always 15. That doesn't change, it's the water level that's changing. So you don't wanna look at this and say, well, the tank doesn't change, so dr dt, dH dt are zeros. We can't do that. But what we could do was use that idea of similarity. So the tank and the water in the tank are similar. And the reason why we have to do this way is because otherwise we're not going to be able to find any of the things that we're interested in. So capital R, they said that was the radius of the tank. Capital H, that's the height of the tank. And that's going to be proportional to the radius of the water in the tank and the height of the water in the tank. And this does 2 things for us. One thing that it does for us is it allows us to say that we have a radius of 5 and a height of 15 for the tank. That equals an unknown radius of the water in the tank and a height in the tank of 2 centimeters. So the first thing this does for us is it allows us to conclude what the radius is. So the radius is 10/15 or 2/3 of a centimeter. So that's one really useful thing that we can do. The second and equally useful thing that we can do with this piece of information is remember that if we cross multiply, we have 5h, lowercase h, equals 15r, lowercase r. So 5 dH dt equals 15 dr dt. And this then gives us every single piece of information that we need in order to write our equation. What do I mean? Well, we know what dV dt is. dV dt is 2 cubic centimeters. Then we've got 1/3 times pi times the radius, which is 2/3 squared, times dH dt. Remember, dH dt is what we're solving for. Plus 1/3 pi times 2 times 2/3 times h, which is 2 the first time, times not dr dt, but 1/3. I'm sorry, not 1/3. Yeah, 1/3, sorry. 1/3 dH dt. And we have then two terms, dH dt, that we're interested in. So I'm going to show off a teensy bit and do this without a calculator, probably incorrectly, but who's to say, right? It's just math, nobody knows. 2/3 squared is 4/9. That's 4/27 pi times dH dt, plus 1/3 times 2 is 2/3, so that's 4/9 times 2 times 1/3. 4/9 times 2 is 8/9 times 3 is 8/27 pi dH dt. So 2 equals 12/27 pi dH dt. And this is where the algebra does get a little bit tricky. This h right here, remember that h is in the numerator. So you have to divide both sides by pi. So when I do that, dH dt, I'm dividing both sides by 12 pi. So I have 12 pi and then a 27 times 2. And before you type this into your calculator, one last warning. You're going to want to use parentheses when you type it in. Otherwise, it's going to come out wrong. It's going to come out as 27 or times 2, which is 54. It's going to do 54 divided by 12, and then your calculator is going to multiply that by pi, which is not what you want to do. You want to do 54 divided by 12 pi, and the units here, what are the units for height? Looks like centimeters per second. Nice. And then you'll have a chance to go through and do 16 again, this time with a height of 12 centimeters. So I'm going to pause here and then talk about that last question. And then that'll be the last bit for recording today. That last question, how do you account for this difference? And the way I think about it is at the bottom of the cup, the cone, conical cup, that's what it is. At the bottom of the conical cup, you have a very small amount of volume, right? That's a very small amount of volume. And as you go higher, you have more volume. So what happens as you go higher is the water is spreading out on top to cover more surface area as you get higher. Like those circles as you go higher are larger and larger. So you're putting in the same amount of water, but it's getting spread out further horizontally. So you go from a really tiny cone down here, which doesn't take very much water to fill, to a much larger cone up here, which takes way more water to fill. And since we're filling at a constant rate of 2 cubic centimeters, it takes longer for that amount of water, like more time for that amount of water to like have made a new height here. So that's why you'll notice that the dH dt at 2 centimeters is going to be larger than the dH dt at 12 centimeters. So pretty nifty.